All right, everyone. We're gonna go ahead and get started here. So thank you all for being here. This is session 1 of a multi-part series that we'll be doing throughout this academic school year. And so we have people from the Storm Prediction Center here to give a good overview of some background and synoptic meteorology and things like that. So like I said, this is session 1. We'll be doing multiple throughout the year. And so, yeah, anything to add? Or with that, I'll go ahead and hand it over to Andrew Moore from SPC. You don't have to use the mic if you don't want, but
I get a shot.
Okay.
Thank you. Yeah, good evening. Thanks for coming out. It's really exciting. So my name is Andrew Moore. I'm a forecaster at the Storm Prediction Center, and I actually was an OWL student many years ago. So I've been in y'all seats, and so I know that going through the OU curriculum, you kind of come out at the end of your senior year, and you're like, I kind of know something about the weather. I kind of know how to derive equations. Cool. How do I use this? And then you go off to your first job. You get put in the forecast desk, and you're like, oh crap! I'm not very good at applying what I learned. So you have all this knowledge, but the application, admittedly, is kind of a weakness of this program. I think, in fact, all of us here, we've all been through this. We've all been in your shoes, and we know kind of how to fill in the gaps, so to say. And really, that's the whole reason for us being here is like, we want to help you guys fill in those gaps and give you the tools to apply what you're learning in the classroom. So, if you're a freshman right now, a lot of this stuff today might just be like super scary math. We really tried to minimize all the math we could. That's okay. Just take it, kind of keep it in the back of your head and say, okay, I see the tools right now. I kind of know maybe how to use them a little bit. I'll learn the math later. That's great. Seniors, some of this might be a review. That's cool too. Use this time to kind of just reinforce what you already know and start applying it so that once you get out to the workforce next year, you're like, all right, I can rock and roll. I can make a forecast. I feel good about it. And so that's, kind of what we're going to be doing for the next couple months. Tonight, we're going to be focusing mostly on the basics. How do we look at a surface chart? How do we look at upper air charts? How do we use them? How do we look at soundings? And then as we go through the year, we're going to start applying more layers to it. So we're going to apply it to severe weather, to winter weather, to fire weather, because these are the big topics that are still forecast challenges today. So that's what we're going to be focusing on. And like I said, tonight, we're going to be kind of focusing on the basics, but there should still be some really useful information in here. And so you don't get much more basic than just a surface analysis. And I hear a lot of National Weather Service meteorologists say, oh, we don't need surface analysis anymore. We've got the mesoanalysis grid. We've got the RTMA, which is like a fancy version of the mesoanalysis grids. And that's true. Okay, I will admit that is true. You could go into your forecast shift, or you could wake up the morning before a storm chase, pull up the mesoanalysis page, get an idea, oh, here's the surface low, here's the cold front, great. But there's problems with that. And the problem is that they're not always correct. They're generally correct, but they're not always correct. And sometimes they can miss details that are really important for when you're trying to make a forecast, especially when it comes to high impact weather. Let me just give an example. Right here in central Oklahoma, we are notorious for one thing in the winter. What's that one thing?
Versions.
No, that's true. Okay, so who was here in 2021? This time, 2021. All right, so what happened in October 2021? Ice storm. Yeah, that's a huge one. So we have ice storms come through central Oklahoma all the time. What's the most important, probably the most important meteorological factor near the surface in an ice storm?
Inversion.
Yeah, close. How about just at the surface? Yeah, inversion's a good one. Let's think about surface only. The temperature, yeah, you need it to be freezing or colder to get ice at the surface. How accurate do you think a 40-kilometer analysis or even a 3-kilometer analysis is going to be trying to get the exact location of where the freezing line is? As sometimes it's good, sometimes it's wrong. And when you're trying to make a high impact forecast like an ice storm, just a few kilometers, a county or more can make a huge difference, especially if you're forecasting like for the OKC metro. Are we going to be covered in ice? Are we going to get rain? That's a big forecast. Same thing with severe weather, gets really nuanced really quick. So surface analyses are still really important. Like I said, we need to know what's actually going on at the surface. We can use models, we can apply some surface observations, use objective analysis techniques, which is just a fancy way of combining a model and surface obs and get something close, but they're not always going to be correct. Looking at the observations actually gives you the exact values. Disregarding measurement errors, that's a whole other thing. It helps you identify fronts. Again, an analysis may not pick up outflow boundaries. It may not pick up the exact location of a front. Let's say you're out on a storm chase and you're seeing an outflow boundary in the Oklahoma mesonet observations, but it's not being picked up by the latest HRRR run. Which one are you going to trust? Are you going to trust the mesonet obs that are showing you the outflow, or are you going to trust the HRRR that doesn't initiate a storm? That's the kind of detail that a surface analysis will actually tell you, help you make a better forecast. And I wanted to kind of finish off with this quote. Many years ago, I heard a forecaster kind of explain this to me, and I thought it was fantastic. But he's like, think about all the best professional athletes you've ever thought of. So like Michael Jordan, Tom Brady, Tiger Woods, Roger Federer, name your sport. You could think of someone who was at the top. Think about how they got to the top. It wasn't, there was some innate talent for sure, but it's also hours upon hours of repetition and practice, looking at, what they're doing. So take Tom Brady. Think about how many passes in practice Tom Brady had to throw to where he was winning Super Bowl after Super Bowl. It took a lot. And you're going to hear that theme come up a lot because with forecasting, it's the same thing. It just takes a lot of practice. And so as with any athlete, they have to warm up. They have to take those practice throws before they go into the game. Doing a surface analysis is our equivalent of warming up. It's to say, okay, let's start working our muscles, get an idea of what's going on, and then see where it goes from there. And also, this is going to tie in really quickly to what we're going to talk about in the next section. So in a little bit, we're going to be talking about upper air patterns. And I'll tell you right now, the surface pattern and the upper air pattern are very intricately linked. They influence each other tremendously. So if you can understand what's going on at the surface, you're going to understand what's going on aloft much better. And that's going to help you make a better forecast and help build your intuition for how the forecast might pan out. So yes, these are absolutely still relevant. Well, let's get into it. So again, this might be a review for a lot of people, but we're just going to cover all of our bases. So we'll take a look at the top right of that screen there, and we're just going to start off by thinking about what does a surface observation tell us? So in the top left, we have our temperature. Bottom right, dew point in America, it's typically in Fahrenheit, not Celsius. Top right, we have our pressure, mean sea level pressure. General rule of thumb, if you see a 0 or a 1 as the first number, add a 10 in front of it. So for example, this would be a 1013.1 millibar surface pressure. If it's a 9, or if you see a 9 there, or sometimes an 8, put a 9 out in front. So if it's like a 980 low, just add an extra 9. I think this might make a little bit more sense drawing it out. So let's say we have, again, here's a dead marker. That's what we have here. Something's never changed. I've been here for almost 10 years now, and this kind of crap always happens. So frustrating. Yeah, so we have our, what? It's true though, right? Also, you have to forgive our rants. SPCers are famous for our rants, so you'll probably hear a few of them. All right, so here's our surface pressure. It's you see it as the 131. Okay, so there's not an 8 or a 9, so we're going to add a 10 out in front of it, and we'll add a decimal to the last one. So this is a 1013.1 millibar pressure. Let's do another example really quick. So let's say we have 980. All right, so this is a 9 or an 8, so we're going to add a 9 out in front, add the decimal at the end. So there's our 998 millibar pressure. And so we do this. This is just a normal convention. It's really just a way to save space because otherwise the plots get really clustered really fast. And so in a second, when we do some charts, you're going to see these. So I just want to make sure everyone's kind of familiar with this idea. The wind barb should be somewhat self-explanatory. This is the wind direction that's blowing towards. You can see right here, we have the long barb and the short barb. The long ones are 10 knots. The short ones are 5. Occasionally, you'll see a pennant, which is the draw one here. So there's our wind thing. It'll look kind of like this. It'll be filled in. This indicates 50 knots. So this is a pretty remarkably strong wind speed at the surface. You don't see these too often at the surface, typically up or above at the upper levels. So that's how we look at a surface station. So the next thing I want to touch on really quick is contouring. So in principle, this is really simple. In practice, it gets really complicated really fast. So let's say, for example, I give this example up here. So we have a station right there, maybe a station here, station there, another station. So we have some stations and they have a temperature of like, that's a 9. Trust me, it's a 9. 992, let's say this is 88 and I don't know, 89. All right, so we have this temperature distribution, and let's say we're drawing the 90-degree isotherm. So what we're going to do is we find, some observation that matches the isotherm that we're drawing. So in this case, we're drawing the 90-degree isotherm. Here's a 90-degree number. And then we just look and say, okay, so we know that temperatures are continuous. They aren't just random breaks in the atmosphere. So that means that somewhere between the 88 and the 92 and the 89 and the 92, there has to be a 90-degree temperature somewhere in here. And so we're just going to take our best guess of where that 90-degree temperature is. So for example, a 90 degrees would be directly in between 92 and 88. So we can say, okay, 90 degrees should be somewhere right here in the middle. And then between 92 to 89, well, that's probably going to be skewed slightly closer to the 89 rather than the 92. So maybe it's right here. And then you just connect the dots. So we have a 90 here, and then we just go down just like that. So again, conceptually, really simple. It can get really complicated, especially in areas where you don't have a lot of observations. But that's the general idea. And so there's a couple of ISO lines that we typically draw. So the first one is isobars, or lines of constant pressure. So this is where you're going to do your pressure analyses. It helps you identify our highs, our lows, surface troughs, boundaries, that kind of thing. The example I just gave was an isotherm, lines of constant temperature. Isodrosotherm, which is a really fun one to pull out at family dinners. So at Thanksgiving, you say, I drew isodrosotherms. They'd be like, oh, this education's paying off. So those are lines of constant dew point. And then finally, of course, our fronts and boundaries. So cold fronts, warm fronts, outflow boundaries, that kind of thing. One optional one that we won't really dive into today is a streamline analysis, which can help identify areas where you have confluence and difluence at the surface. So if you want more details on that, come find me. I'd be happy to talk about it. But we'll focus on the main ones for today. And here's some just general guidelines. I'll just make a quick comment. So I say here, contour every 4 millibars, contour every 4 Fahrenheit or 5 Fahrenheit. The reason typically, historically, people do every 4 Fahrenheit. And the reason for that is that say you're drawing every 5 Fahrenheit. And then you get to a spot where it's like, man, I really need more detail in here. I need to start doing tighter contours. Well, if you're going to split it in half, you have to go to every 2.5 Fahrenheit. And that gets really complicated because you got to kind of figure out, okay, well, that's like halfway between this. If you do it every 4, then okay, you can just drop down to every 2 Fahrenheit. Or if you want to do more sparse, you can go up to 8. So you can scale it much easier than you can every 5. I'll be honest, I typically do every 5 because I really suck at mental math, and 5 is a lot easier for me. So, and everyone does it slightly different. Figure out what works best for you and just run with it. All right, so here's an example of what one might look like. So we have our surface plot up here. Again, here's all of our surface stations, really similar to what we just talked about. And I've gone ahead and I've drawn on the isobar, so the lines of constant pressure. And so from this, we can kind of get a sense of what's going on. And so we have some kind of trough feature right through here, and I added a little low symbol. So one thing, this is me personally, what I like to do, so don't have an eraser. That's all right. Right there. Oh, perfect. Thank you so much. Yeah. So one of the first things that I do whenever I start my surface analyses is I kind of look for areas for swirl. I look for surface lows because they're easy to identify and you can kind of work your way out from there. It makes it go much faster. So the first thing I look for is areas where the winds are generally convergent like this. So that's the general wind pattern at the surface that I'm looking for. That catches my eye first. And then I start here and start looking, okay, what's the lowest pressure that I can find? And so on this map, I know it's really hard to see. I don't expect y'all to be able to see it. So I'll just tell you, but right in here, you can kind of make out that we have that convergence pattern at the surface. Okay, my eyes are going to go there. And I see we have 1006, 1006. I think that's a 1062, 1070. So right in there is some kind of surface low. That's the lowest pressure that I'm seeing. So I'm going to start there. Maybe I start at 1006. In this case, I started at 1008 and went from there. Personally, I started at 8 or 12 and go that way, or whatever the lowest pressures I can find. And then I just do every 4 millibars. But these kind of features, again, that's really helpful. Try to look for those, identify them. because typically there are boundaries in the vicinity of our surface lows, and those are typically important for severe weather forecasts or other forecasts. So these are the kind of patterns try to look out for. All right, so we have our isobar analysis. We found the highs, we found the lows. So let's do our isotherm analysis. So this is kind of where it gets a little bit messy. I'll be honest, this is not very clean. It very rarely is very clean. But once you start to do these, you'll start to pick out the signals that are really important. And I'll just point one out here. It's kind of hard to see, but if you notice, there's a plume of higher temperatures that goes up through central Oklahoma and to Kansas and into southeast Nebraska. Okay, so that little plume of temperature, let's draw that on here. Kind of looks like this. So what this is saying is that we have really, all right, hot temperatures here. So here's our hotter temperatures. What would be just to the east of this? Is it cooler or hotter? Yeah, it's cooler. So that's our cool air. So what do we typically have between our hot air and our cool air? Front. Yeah, front, exactly. So we know now, okay, we've identified where our thermal axis is. Somewhere in here, there should be some kind of boundary. Maybe we aren't sure exactly what kind yet. Could be a dry line, could be, I'm sorry, it's not gonna be a dry line. It's typically a cold front, right? But that's kind of how we start to build our intuition of where some boundaries might be and what kind of boundaries they might be. Same thing on the north side. If we see this thermal plume coming up and we think, okay, here's our hottest temperatures. Up here, it's typically cooler. So somewhere in here, there's another boundary. And typically, this is where we see our warm fronts emerge. And so now we're starting to build our picture of, okay, now I'm starting to figure out, I've got a surface low, I've got my warmer air coming up, I've got a warm front, I've got a cool front. Now I'm starting to build an idea of what the cycle and model looks like. Now you can start to make some really good ideas of maybe what's going to happen in the next 12 to 24 hours. Yeah, that's all I wanted to say there. So we'll go to the next one. So that fun word, isodrosotherm, dew point analysis. So why might a dew point analysis be really helpful in the southern plains, like in Oklahoma? Dry lines, exactly, yeah. So typically you're not going to see a very big, gradient in the temperatures on a dry line day, but you will see a really big gradient in the dry or the dew points on a dry line day. Really common out here all the way up really through much of the plains. So here we kind of see, okay, there's a really good gradient in dry or in dew points from central Kansas down to northwest Oklahoma. But in this case, we've kind of already identified that there might be some other boundary taking place there. There might be a cold front. So this is where doing both of those analyses kind of comes in handy. If you did the isodrosotherms first and did your dew points first, and you saw that tight gradient, you might be, oh yeah, we got a dry line today. Awesome. And if you didn't do the isotherms next, you might mistakenly identify it as a dry line when in fact it's a cold front. And as we'll get into probably in the next session, storm behavior is much different when you're talking about a dry line versus a cold front. So that detail is really important. All right, so the next, as I mentioned, we're going to identify our boundaries. So as we talked about, we identified there was a cold front coming through here. I went ahead and just identified a couple of other kind of weaker warm fronts that I noticed. And sometimes it's really difficult to identify what kind of front it is. Maybe it's just a weird surface trough or it's a confluence zone. If you're not sure what kind of boundary it is, that's really okay. Go ahead and mark it. Just noticing that something is there is probably the most important part. And as you go through the day, you can start to pay attention. Okay, how is this boundary behaving? Is it behaving more like a cold front, an outflow boundary? Maybe it's acting more like a warm front, but just go ahead and mark it because it could be really important. All right, so now's the fun part. Here's the first of many quizzes that will be coming at you through these forecasting sessions. So we're going to do our own surface chart. So if you got a pencil or a pen, bust it out. But really quick, so what we're going to be doing, we're going to pass out two maps. It doesn't matter which map you get. We're just going to be focusing on doing a frontal analysis. So focus on finding the cold fronts and the warm fronts.
Map one.
Yeah, we'll do them both.
Oh, you want to do both?
Yeah, there's enough people. Just Okay, let's reconvene. It's okay if you didn't finish. We're going to talk about all these. All right, so who in the room had map one? Raise your hand if you had map one. I think it's mostly this side. Cool. Who had map two? I'm guessing, yeah, everyone passed out papers too. All right, so both of these maps, they're very different. One of them, I will admit, is much easier. Map 1, congrats, you got the easier of the two maps, in my opinion. Map 2, or group 2, congrats, you did a harder surface analysis. So if you're a little bit confused, that's okay. We're going to talk about both of them. Map 1, people, though, I really expect a lot out of you. This is the real test. It's for you guys. So here we go. We're going to talk about both these maps and some of the forecast implications that happen on both these days. All right, so here's map number 1. You guys should know it. Does anyone want to talk about what they see in map 1 so that the map 2 people can kind of get an idea? Any volunteers? Yeah, go for it.
All right, so we got a surface. Okay, we got the surface slope probably. It's in Nebraska. It's right there. Perfect.
It's general region.
And so there's 2 things I noticed. One is a trailing cold front. Well, 3 things, but first is the trailing cold front, and the cold front is kind of weird. It starts going to Kansas and kind of bends back, and the secondary surface low in southeast Colorado. And so there's that whole kind of boundary there. And then there's a dry line that extends ahead of the cold front going through central Kansas and central Oklahoma down into Hill Country, Texas. And then there's a warm front that extends east, east of the surface low through exactly.
Back through here somewhere.
Yes.
Yeah, that generally.
Yeah.
Cool. Any other details about map 1 that are noteworthy?
There's a kind of a cold front-ish in the north of Florida.
Okay, so back down here.
Yeah, looks like some sort of occluded surface low. You could also call
Cool.
it stationary front. It's probably stalling.
Yeah.
Yeah, there's a hot, looks like maybe a high over Utah. I'm gonna stop talking.
No, that's perfect. That's great. Yeah, map 1 ideas.
There's a warm front stretching east from the surface low in southwestern Nebraska. And then like through southern Iowa.
Yeah, right in through here. Yeah, very good. Yes, sir.
You want to be really picky. There is kind of a warm frontish feature that is in Oklahoma, where you go from 70s to 60s that goes from the low into central Kansas and then it's back in central Oklahoma.
So you're seeing like the 73 here into the 60s here, somewhere in there. Okay, no, excellent. And that could be really important. All right, so very good. Cool. So what I'm going to show you next is not my analysis. This is the analysis from WPC. So if it's wrong, we're going to blame them. So, but it was much easier to show this in a clean way because you don't want to see my scribbles. It would not be pretty. But this is what WPC had for about the same time as these observations. And so map 1 people, what are some things that the WPC map may not have, may got wrong?
Is this behind where this map is?
This map is at 1638. Those obs are at 16Z.
Okay.
So roughly the same time.
That dry line is too far west in my opinion. I feel like it's stuff because if you look at the wood chip.
Yeah, let's jump back to the obs.
Probably have it in Kansas.
I mean, maybe it's just a diffuse dry line. It's not as like sharp as like you would. It's as
Yeah. So here's a question for my map and my map 2 people. So everybody. So let's actually focus on Southwest Oklahoma because this is actually could be really important on big severe weather days. So let's look right here, kind of towards the Lawton area. Dew points are in this mid 60s, like 64. Let's go out to Childress, Texas, right here. Dew point is 61. So are we through the dry line yet?
No.
No. What kind of wind do we have at Childress right here? Southwest. How about back towards Lawton? Southeast. So it's not a dry line. What's going on there? Yeah.
It's a convergence band.
Yeah. And so let's look at our, that's very good, by the way. Double checking. What else could it be? So yeah, confluence is great. There's another phrase for that. Surface pressure trough. Yeah, excellent. These can be really tricky and they're often missed. If you go back and read like old storm chase archives from like back in the day, they often talk about how people will go too far west and all the storms initiate further east behind them because they're initiating in the surface pressure trough. So that can be really important. Just little things to notice. So yeah, the dry line's back up to the west, but we're seeing that confluence axis in Southwest Oklahoma. So that's interesting. Those are important details. And let's go to the WPC map. Do we see that feature there? No, they totally left it out. So you can't always trust other people's analyses to get it right. You got to look at it yourself. And that's kind of the point of this exercise. So for those interested, this date was October 12th, of this year. So just 7 days ago, last week. Does anyone want to guess where the EF2 tornadoes occurred?
Florida.
That's right, it's in Florida.
Yep.
What's going on in Florida?
So remnant tropical cyclone and surface low that had NUC probabilities that enhanced the low level jet that had these low altitude cells in clear water.
Yeah, we'll get more into details on the severe part of this. This was just kind of a little head fake that the actual main threat was actually displaced from the obvious surface feature out in the plains. But there's also a secondary story I want to talk about with map 1. And this is what kind of prompted my pseudo rant tonight and why I'm hammering so hard on surface analyses. So in the Weather Service, we have ways that we can see, it's like basically a chat room. We can see everyone chatting between each other. And I won't name people, I won't name the office. There were some offices that were dealing with severe weather that were having a hard time making warning decisions because they were misidentifying where the storms are, like which air mass they were in. So the storms were actually displaced well to the west of the surface low. They were back to the northwest of the low, back in this area, this part of Nebraska. They were kind of struggling. They were thinking, hey, we think there's a tornado threat here. The winds were out of the northwest. It was cold. It was getting colder. They were behind the cold front. That's not very conducive for tornadoes. We'll learn why later. But it's because they didn't do a proper surface analysis in real time. And so they were misidentifying the environment and they were getting, having a hard time. And so if they had done the surface analysis the proper way initially, it would have been a lot easier for them. All right, so that's map 1. I'll stop going crazy about that one. Let's go on to map 2. So my map 2 folks, here's your observations. What can you tell us about map 2 for our map 1 friends? Yes, sir.
Generally like a pretty benign surface pattern. It looks like you have a lot of high pressure dominating the eastern third of the US. You kind of make out sort of a diffuse dry line. It's probably sharpest in the Texas Panhandle and base in Oklahoma Panhandle, southwest Kansas. And maybe some sort of cold front up north in Montana, North Dakota. But in general, there's not too much. You don't have very strongly sort of synoptically forced sort of surface flow, it looks like in this map. And I didn't do the isobar analysis, but in general, it's sort of a pretty chill day.
No, that's a good description. It's really diffuse. There aren't any. Yes, sir. Yeah.
Also, what looks like sort of could be an outflow boundary in northwest Missouri. There's a wind shift, and then the observations also show some clouds over rapid.
Yeah, like right through here.
A bit further south.
Oh, back through.
Like northwest corner.
Oh, back over here.
Yeah.
Yeah, no, that's definitely possible. This ob right here is reporting rain. So yeah, it could be something going on there. Good observation. Yeah, so this is an example of a day where it's really kind of hard. Honestly, part of this exercise is just to show that identifying these boundaries, sometimes it can be really tough. And it takes a lot of time looking at boundaries to identify what kind of boundary is this? Is this a surface trough? Is this a cold front that's just become really diffuse? It can be really tough. So again, here's the WPC analysis. Does that kind of match up with what you were thinking? I'm seeing both nods and no's, yeses and no's. So what are some differences you see here? Map 2 folks, any differences that are notable?
I'm kind of surprised there's not a draw line with them with troughs. Just I did see kind of a new point there. It's not too massive. I guess they're out of floating water, so there's too much different than on the east side.
Yeah, so that's a really good point. So he was talking about how he was surprised there wasn't a dry line analyzed here. The other way that you can describe doing this process, it's sometimes called subjective surface analysis, and that's where the subjectivity comes into. It's like you have to decide what kind of boundary it is. But again, you have to figure out what kind of boundary and get it right to get the right kind of forecast. And so, yeah, this isn't always super straightforward. Sometimes this is really tough. So map 2 people, again, I apologize. Y'all got the tougher of the 2 maps, but good job on taking on a tougher task. But this is what the real atmosphere looks like. It's very rarely as clean as the map 1. Those are the exceptional days. Most days look like map 2s. And so this is the final takeaway, and then I will stop talking. But this is the biggest takeaway that I want you guys to take away from this exercise and really for this entire night is that it takes a lot of practice. All these concepts, you have to practice them and practice them. And the biggest pitfall I see a lot of forecasters fall into is they wait until the weather gets interesting to start practicing, and that's too late. You got to practice when the weather's quiet and there's no consequence if you get it wrong. The high risk day, when you're forecasting an outbreak of tornadoes, that's not the best day to start trying to remember how to do a surface analysis. And I've seen that happen sometimes. Back where I used to work, it has happened. So practice now, get really good. And by the time spring comes around, you're going to be knocking them out in 10 minutes. And it's going to go really smooth. So, yes, sir.
Throw in too, like, practice doesn't have to be a ton. If you do one map a day for 2 weeks straight and you are consistent with that, you'll be amazed at not only how easily it comes, but how much faster you get with it. So it doesn't have to be a lot of practice. If you just do one and just repeat that over and over and over, it'll get easier with time. So set a personal challenge, stick to it, and see what happens.
Good things will happen. Nothing bad typically happens from practice. With that, are there any questions? Otherwise, Robbie, do we want to take a break, or?
Yeah.
I'll let you make the call.
Yeah, we can go ahead and take a break.
Do have one comment to throw in. If I hadn't been introduced, I'm Rich Thompson, one of the senior leads at SPC and an ancient OU grad. I'm not trying to throw our sister national center under the bus.
Yeah, sorry. Yeah.
But call up the HPC analysis. I mean, is that the best you think you can do? This is somebody on a time deadline, and look at the number of observations plotted. These are not senior forecasters at the center doing this. So the question is, do you think you can add value to an analysis like that? So I personally never, ever look at these because I know I can do better. And
It's on the under bus.
Okay, I'm not backing over them more but I think that there's a lot more detail in there than you can reasonably expect someone from a national center on this deadline that's not interested in the details. They're not having to make a forecast. This is just to put out you're staring at the weather from, halfway to the moon. Most of your forecasts are not going to be made that way, even at a national center. So you can see that I'm sure you have a lot more details in your analyses, especially this map 2. I have twice as many boundaries as they show, and some of these are going to be important. So it just encourages you that there's a method behind this. If you just let them do it. Who are they? I mean, I don't know. Maybe it has a name, but some of the people I like that. The question is, do it yourself and rely on your own analysis. That's what's going to make it better.
It's just WBC.
See, I only got so one slide.
Doesn't say it's that.
Yeah, thank you guys. Yeah, so I guess we'll go on break. If you have any questions, feel free to come down, and we'll keep on rolling after 10 minutes or so.
All right, guys. Who's ready to learn about why troughs and ridges be doing what they be doing? Yeah. All right, guys, let's bring it back. Yep. No, we're not gonna do it. What's up? Yeah, I do need a gavel. Yeah, I could just yell really loud. All right, guys. Hey, I'm Andrew Lyons. I'm also a mesoscale assistant fire weather forecaster at the Storm Prediction Center. There's not enough Andrews. There's 4 of us there. So if you're named Andrew, you got a good chance of getting hired there. So yeah. But I wanted to talk to you guys today a little bit about something called quasi-geostrophic theory, or QG, if you've heard of that acronym before. So we just talked about surface analysis and why that's really important. But have you ever wondered, why is the surface low actually there? Anybody? Yeah? Well, this might be able to tell you a little bit of why. So QG stands for quasi-geostrophic theory. Yeah. What's up? Is it going on?
I guess I don't remember actually.
I started it. Yeah.
Oh, you did? Okay.
Yeah. I think.
Yeah, I think that's the thing.
Say, okay, all right, cool. We can't deprive the people on the internet of this, so. But QG is, in reality, just a simple framework. Well, I say simple, the math behind it is not simple, but we will not be doing any of that today, so you're all welcome. but it's really just a simple framework for understanding changes in vertical motion and pressure or height tendency in the atmosphere. And we'll go over why some of that's really important and what information you can actually glean from it. Because from this really simple framework, you can actually learn a lot about the atmosphere and predict a lot with some really simple rules. So, like I said, it's complicated mathematically, but we'll break it down and we're just going to do some scale analysis type things that'll show you, hey, which term is positive, which term is negative, and how that all fits together. So seniors and juniors, you guys may have done some of this already, but underclassmen, this will probably be your guys' first introduction to QG. We can always talk about the math more later. There's actually a really good video lecture series by Ariel Cohen, who is another Storm Prediction Center forecaster, that actually breaks down the entire math behind it. So if you feel like deriving a bunch of equations, go for it. But some of the questions that we might think about in a QG framework, why do troughs move from west to east? Anybody ever thought about that? I mean, the wind blows from west to east, but is the wind blowing the trough? I don't know. And why do ridges cause sinking air beneath them? Have we ever thought about that? You can actually answer all of those questions using QG as a framework to think about that. Okay. How many of you have heard the term vorticity before? Good. I see a lot of hands. That's okay if you haven't, because vorticity is kind of this abstract concept, but it's actually really simple. All vorticity is the amount of spin that a local particle within a fluid flow has. That's it. It's just the amount of spin that something has flowing through a fluid. A lot of times you'll see vorticity depicted like this on a planar chart. So you'll see you got a trough of lower heights there, and then you have vorticity in units here at the bottom. And all that indicates is the amount of spin in the air at that level, at that location. That's all that means. A really good way to think about vorticity is if you had a pinwheel in a stream of water. And if you look at the spin of the pinwheel in the stream of water, which we'll go ahead and animate here. So if you've got a straight flow, right, and the water is just moving straight away, the pinwheel won't spin. So it'll just go with the water, but it won't spin around its axis. That's zero vorticity. But if you've got a stream of water where there are differences in how fast the water is moving on one side, say on the bottom side, you can actually get, oh, I forgot I had that sick animation in there. If you have a difference in the flow speed, it'll actually cause the pinwheel to spin as it continues through the water. You see kind of how that changes with the arrows there? The pinwheel is actually spinning with time. And that's called vorticity. That's all that is it's just the spin of that particle. Now, this is something called shear vorticity, and there are actually two types of vorticity. There's something called shear vorticity and curvature vorticity. So in a local fluid flow, if we have water that's moving at different speeds that causes spinning, that's one way to get spin. How do you think curvature causes spin? I'm just going to pose that question. Think about it. Anyone? Yeah. Yeah. The water is curved. Think about, we just talked about the stream, right? If the stream is straight and the pinwheel is going with it, then there's no vorticity. But if the stream is curved, like in a trough, if you have a stream of air that's curved, that actually still causes the pinwheel to spin. It doesn't spin relative to the fluid flow, but it spins relative to the framework that you look at it from. That's curvature vorticity. So vorticity can be broken down into shear vorticity and curvature vorticity. Those are the two most common things that we think about. And we'll show some more examples of that, but be thinking about that pinwheel in the flow as kind of your reference frame for that's how you get vorticity. And then, yeah, it spins. So, woo! All right. Another really important concept. So we live at the surface of the earth, or at least I hope most of you do. But when we're thinking about wind, a lot of times we're thinking about wind that's blowing horizontally. We don't often think about wind that's moving vertically. But vertical motion, it has its ups and downs. You're welcome for that. That's really what's causing a lot of the more interesting aspects of weather. So when you're thinking about atmospheric dynamics and forecasting in general, I don't want you to think in 2 dimensions. I don't even want you to think in 3 dimensions. I want you to think in 4 dimensions. So you've got your 3 dimensions in space, but you also have your dimension in time too. So vertical motion over time is really important in meteorology. So I want to go over some quick terms too, but really all I want to get home across in this point is that you need to be thinking about not only air going from side to side and up and down, but also how all that changes in time. How many of you guys have heard the term advection before? Okay, good, yeah. Advection, a really simple definition, it's just the movement of heat or matter by air or fluid, and it can be horizontal or vertical. A lot of times people think vertical movement is all convection. It doesn't have to be. You can actually advect things vertically, but advection is a really important term. And then of course, convection, this is the vertical movement of air as a result of differences in density. So this is your prototypical thunderstorms, right? You get convection because you have a bubble of air that's warm and moist, that's less dense than the surrounding air, and that goes up too. But those are the 2 different types of motion that we want to describe. We're going to be mostly dealing with advection. So things that are not convective, things that are moving as a result of dynamics and physical processes that are not related to differences in density. At least initially, you can actually do that with convection, and that gets really complicated, and I'm not smart enough to describe that to you. So, all right. So we talked about vertical motion again. Let's just go through some of the things that we're looking for. So vertical motion can cause clouds. It can cause precipitation. It can also precondition the environment for storms. So if you think about the ingredients that you need for severe weather, how many of you guys have heard this acronym, LIMS or SLIM or something like that? Yeah, that's the ingredients that you need for severe weather: lift, instability, moisture, and shear. So vertical motion can influence all of those, and it's really important. So even nice weather, your high pressure. Today was a good example, nice and sunny. That's probably a result of vertical motion because you have higher pressure that's suppressing cloud development, convection, things like that. So your nice, sunny, warm days during the summer, a lot of times that's driven by subsidence. So I like to just sum it all up, but all the fun stuff in weather happens because of vertical motion. So it's kind of what's going on. So be thinking in that 4-dimensional space, 3 directions, X, Y, and Z, and then time. Okay. I'm gonna ask again, how many of you guys have heard the term thickness before? Yeah. Okay, in a meteorological sense, like, not like, I don't know, but meteorological thickness is just a way to describe changes in layer heights, right? So the layer between, say, 1,000 millibars and 500 millibars, but that's really just related to the pressure within that layer. So pressure is the weight of the atmosphere over the depth of the column, right? So it's literally the weight of the air above you. What kind of things can change pressure? I heard someone just say it. I believe in you. Say it loud. Temperature. There you go. Yeah. Okay. The mean virtual temperature. Yeah. I did say I would call on the grad students down here, so I will pick on them. But yeah, temperature. That's one of the biggest influences of pressure. If you remember your basic ideal pressure gas law from chemistry and all that. Increasing the temperature of a sealed container, what does that do? Increases pressure, right? It causes things to expand. That's how you blow something up. Don't blow things up. And if this conversely, we shrink things by cooling them, right? So if we've got a layer of air that we cool, a lot of times you can shrink that column. Just thinking about some of the terms that we just talked about, how do we start to move temperatures around in the atmosphere? There's a word that starts with A. Advection. There you go. Yeah, you can do it with convection again. I'm not smart enough to describe that, so we'll get into that later. But you can actually move substantial amounts of mass horizontally, but that actually affects the vertical atmosphere too, through temperature. So Here we've got a nice warm bubble. Actually, let's go back. So we've got two pressure levels, right? We'll say this is the pressure at the surface on the bottom line, and that P1 is just a pressure level above that. If we stick a nice big warm blob in between there, it actually raises the thickness of the atmosphere. You increase the depth because you're warming that column. Think of it like a balloon. If you're heating up the balloon, you're actually raising that top pressure level. And so you can increase the height, but notice here what happens at the surface. You just moved all that mass above. Yes, height falls. So you can think of this in terms of a difference in surface pressure, but what this actually is saying is that when you have temperature differences or temperature change in certain layers, you can actually influence things above it and below it. And that's going to be a really important thing that we talk about later in this, is something called differential advection. Anyone have an idea of what that means? Just real quick. No?
I'm gonna let the other people answer.
Warm air advection near the surface, and cold air advection a lot.
Exactly. Yeah. It's just differences in the type of advection that occurs. So you can have changes above that type of advection and below that type of advection, depending on that maximum. And that's really important. And so we can run through that same thing. If you shrink that column, if you're shrinking that balloon, you're actually causing the pressure at that height to be lower, and you're actually increasing the pressure at the surface. So this will be really important, how we generate surface lows, what we do to our troughs and ridges in the upper atmosphere too. So again, at the bottom there, warming aloft lowers pressure below that warming, but it actually raises pressure above it because you're lifting that pressure surface. Cooling aloft, or at differential cooling, causes rising pressure below, but lowering of the pressure or heights aloft. So here's just another kind of example. You see they're picking a couple of spots. We just talked about that surface low and that cold front, how you've got colder air coming down. You actually see the atmosphere is suppressed behind it. So it's actually shallower, the thickness is lower, whereas on the other side, the thickness is higher. You've got a warmer atmosphere, you have a balloon in there that's causing it to expand, and you get lower pressure at the surface, near the surface low, and higher heights above that. Does that kind of make sense to everybody who hasn't seen all that before? It's easier to kind of conceptualize once you see it in that cross section. So, but if we get into something that's confusing, just shout it out and stop me, okay? All right. So the first thing that we're going to talk about is something called height tendency, QG height tendency. There are two equations in QG. This is the first one, and this is kind of more conceptually based in that. So all this is going to tell us is how the geopotential height changes with time. So you can think of geopotential height as what you see on those isobaric pressure level charts. So at 500 millibars, all those charts are showing is how high in meters, in geopotential meters, is that 500 millibar pressure level. We want to see how that changes through time. So there's a really good example on this. You see the vertical section there. So that shows all the pressure levels. Then you have a trough. So all that trough is just a lowered area of geopotential height. So it's just a part of the atmosphere where it's been crunched down because it's colder. And we can also talk about the changes in time with that. We can monitor those changes. This is a really common plot that you'll see. This comes from the SPC mesoanalysis page. We use this a lot, but this shows the 12-hour 500 millibar height change. And you can see you've got a big area of negative 30 decameters and then negative 60 right there. So that tells you how far the atmosphere has changed in 12 hours. Why do you guys think that might be important? What did we just talk about with all the thunderstorm ingredients? What's the first one that you need? Yeah. Lift, exactly. Yeah. So changes in geopotential height can cause vertical motion, which supports thunderstorms, precipitation, clouds, all the fun weather, you know? And conversely, height rises, that causes sinking air. So that's how you get your, warm, sunny, high pressure days that you don't have a lot of clouds in there. So you're already starting to see how changes in QG can affect things at the surface. All right, I told you there'd be no math, but there's the math. Yeah, that's an equation. Yeah. You want to talk about a thickness equation? That's, yeah, there you go. All right. So now we're going to derive it. No, I'm kidding. I'm kidding. We're just going to go through each term and kind of break it down. I promise it's not bad. It'll go fast. So that term on the left, this is actually a cool thing that you're going to learn in like what, Calc 3 or 4. I don't even remember. But all that term A is that big scary thing, and then the Greek letter chi. All that big scary thing is a minus sign. So it has to do with trigonometry. And if you square a sine function, or if you take the second derivative of a trigonometrical function, you actually get the inverse. So you get a negative of that. So really, all we're doing is treating that as a giant negative sign. That's it. And then the Greek letter chi, that's our height change. So that's what the field that we're looking for. That's all we want. So that's the change in geopotential height with time. It's just the Greek letter chi. It's a funny X. So yeah. All right. Term B also looks terrible and scary. All that is just the advection of vorticity. That's really all it is. There's some individual things that you have to look at with that, and you'll get into all the math behind that, but you can simply treat it for this purpose as the advection of vorticity. Advection vor. My handwriting is terrible. I don't apologize for it. Term C, again, that looks terrible. I don't want to derive that. Nobody wants to derive that unless you like math, which good for you. You'll all get through it, I promise. All that is just the differential thickness advection. So we talked about thickness. Fiction, yeah, I know. It's just related to the mean temperature in that profile, in that layer of air. So all we can say is that this is just differential temperature advection. Differential temp advection. And then the fourth term, we're going to totally ignore. We don't have to worry about it right now. So all that is it's called differential diabatic heating. So you can think about this as processes that are not adiabatic, so that are not conserving temperature within that. So this is things like latent heat release, if you're dealing with hurricanes or large thunderstorm complexes, but that can also change the height of the atmosphere. So if you've ever seen a thunderstorm complex in late summer, persist for several or more hours and then regenerate itself, that has to do with the differential diabatic heating. The thunderstorms themselves are actually releasing energy that causes the atmosphere to change, and that can actually support that. But for our purposes, we're going to be dealing on the synoptic scale. We're not going to be worrying about too much of that. So that's really scary. But again, if we just break it down into this, that's all these are. The negative height change with time is equal to the amount of spin advection plus differential temperature advection. How much energy are you putting into a layer in the atmosphere over time, plus how much spin over time is related to how it changes in time. So it's actually a really simple concept, and you can look at this all on a map and diagnose these types of things really quickly. And that's exactly what we're going to do. All right. So, oh, there's the brag. Yeah. We've got a really simple ridge and trough, right? So we've got our geopotential height lines. We've got a ridge here. We've got a trough here. So thinking about what we just talked about with vorticity, we're looking at where we would have those values. So thinking about our spin, in the vertical, our ridge is going to have our area of maximum negative vorticity, or our minimum in vorticity, I should say. So that's where all the anticyclonic vorticity is. Conversely, in our trough, at the bottom of our trough, this is where the maximum in positive vorticity is. So, and think about our stream example, right? So if you've got air that's moving through this, you've got curvature. So a particle in there is going to turn with time. That's our curvature. That's the curvature vorticity. And then you also have your wind is not going to be the exact same across that whole thing. And that's your shear vorticity. So your maximum in vorticity is usually here at the bottom of the trough. So thinking about all the processes that we just talked about, let's figure out where there's rising air and sinking air. It's actually not hard. Oh, sorry. So there on the bottom, you see we've got negative height change. We'll just say H change is equal to our vorticity advection or advection. Okay, so let's pick a point right here. Our wind is coming from this way, by the way. I should have told you that. So we've got our maximum or our minimum vorticity right here at the top, and our wind is blowing this way. So what sign is our vorticity advection at this point? What type of vorticity are we moving towards that point? Negative, exactly. Yeah, it's negative. We've got a negative H change against a negative there. What do you get with two negative signs? Positive, exactly. So our height change is positive over time, simply because we're moving negative vorticity to that point over time. So what would we expect our ridge to do if we're slowly increasing the heights with time? Someone said it. Yeah, it gets bigger, but it shifts over there. So we're actually propagating the ridge that way. Okay, let's do it on this side. Keep losing the. All right, so here's our point now, point 2. What kind of vorticity do we have at the bottom of the trough? Positive. If our winds are blowing that way, is the vorticity increasing at point 2 or decreasing with time? Increasing. Yep. So our negative H change is opposite a positive factor. So all we have to do is move the negative sign over there. And our time rate of change of the heights is negative. You guys see how that works? Yeah. So with time, our trough should move to the east. There you go. The heights over here are going to fall with time. All because of that simple relationship. We can actually do the same thing with temperature advection. So I've added the surface low and stuff on there. So we got a surface low that's right here. And we'll say surface high pressure. Yeah, right there. So if we got a cold front that comes off that, what kind of air do we have behind a cold front? This should be really simple. Cold air, exactly, right? So if cold air is coming down like this, we'll just say, we'll move our points here. We'll just say our point is right there. If we're getting more cold air with time, what's that temperature change? Yeah, it's negative. So, but this is a differential temperature change. So we actually have to think about how that's going to change. What did our atmosphere do when we had cold air? Think of the bubble example there. Yeah, right. The atmosphere crunched down. So it went. So this is where that differential part comes into play. If you have cold advection at the surface, you are going to suppress the atmosphere, but you're going to suppress the entire column. But if you have cold advection above the surface, you're going to bring part of the column down, but you're also going to crunch it up like that. So you actually have height falls here, and you can kind of visualize that, how you're taking that down. But the math works out too. So you have that negative temperature advection right beneath the base of a trough. You've actually got height change being positive. I think I've got the other one on there too. Oh, I guess I skipped that slide. But you can do the same thing on the other side. For the sake of time, I'm just going to move on to the next equation here. Okay. So we just talked about the QG omega equation, or sorry, the QG high tendency equation. This is the QG omega equation. So someone said your favorite, yeah. Omega, if you guys are not familiar, omega, the Greek letter, is often used in meteorology to represent vertical motion. So that's where this comes from. So we just talked about the height changes and we talked about the vertical motion. This is the math behind it. So again, we're going to break down the same thing. They're actually really closely related. So the vertical motion, omega, which I'm actually going to change that. So you can think about omega being negative pressure change in time. We're going to think about it as W, which is just dz dt. So all this is saying is that W, your vertical coordinate, you're moving up in time. So that's positive. That simplifies the math a little bit. But your vertical motion is just equal to your differential vorticity advection plus your temperature advection. So it's the same sort of thing, but we flipped a couple of things. Temp advection. It's really similar to the other one. So your changes in vertical motion are just related to the spin advection plus the advection of temperature. So we can go through and do the exact same thing that we just did with that. And there's a scaling for stability. So basically, if the atmosphere is more unstable, it's easier to move things up and down vertically than if it's more stable. Again, there's more complex math behind that. But we've got our simple ridge and trough pattern again. Just do this. Got a ridge. Got our big negative vorticity. Got our trough. Positive vorticity. Where's the point of that? Yeah. All right. So differential vorticity advection. At that point, with the wind blowing, what is our advection bringing us? What type of vorticity with time? More negative. Yeah, that's right. More negative. So we've got that. So our W is opposite a negative sign. So the vertical motion is down with time because we're simply moving more negative vorticity into that location at the same time. But if we go to the other side, and say, what type of vorticity are we moving into that point? Positively, right? So that means that our vertical motion is increasing because we're moving positive vorticity in over time. And we can do the exact same thing with, yeah, there we go. So omega less than 0. I flipped this around, but it means the exact same thing. And so this is the temperature example too. So if we have cold air coming in, we've got cold air coming in from the north. At this point, our vertical motion is offset from a negative sign, and that's sinking air. So behind the cold front, where we've got cold air, that's causing vertical motion to go down. And at the other side too, where we've got warm air advection, it's actually causing rising motion. So all of those simple relationships from all that complicated math tell us is that if we look at a couple of really simple things, we can diagnose where there's vertical motion and where there's going to be pressure changes that impact weather. So you guys kind of following? That's a lot if you've never seen any of this stuff before. So stop me if you're confused about anything, okay? But everybody good? Okay. So there we go. So negative temperature advection, we're sinking motion. Positive temperature advection, we're rising motion. Now, you can have some offset between these two. This kind of gets into some of the complicated stuff where you're not quite aligned, but there's kind of a sweet spot that you can generate where you have temperature advection that's causing rising motion and vorticity advection that's causing rising motion, and that overlaps. And so that can be where you have your zones of ascent. Okay, jet streaks. So right now we've just been talking about kind of regular basic troughs. Kind of with the fluid flowing all the way through it. So have you guys ever seen a jet streak model where it's kind of broken into the 4 quadrants before? Some heads nodding. Yeah. So you can actually apply the exact same concepts that we just did with the troughs and ridges to jet streaks to kind of go through and talk about things. So the fluid here is moving faster than the fluid on the outside, okay? So remember our shear example, right, of the fluid going in through the flow? So if I've got a particle up here and the fluid is moving faster on the bottom, what kind of spin is that going to put on it? If the spin that we think is this way. Positive, exactly. So we've got positive spin up there. And what should we have on the bottom where the flow is opposite? Negative, yeah. So that's just vorticity. That's all that is. It's just vorticity across a jet stream. So thinking about our vorticity advection, if we've got our maximum here, what is the vorticity going to be doing with time over there? Increasing or decreasing? Increasing, right? And thinking back to our QG omega, what happens when we have increasing vorticity with time? Causes rising motion, yeah. So there's rising motion in this quadrant of the jet stream. Now let's look at the other side. So this is our maximum. What happens at this point? So if the jet stream is moving that way, is there increasing vorticity? Decreasing, yeah, it's decreasing with time. So using that same logic, you actually have sinking motion right there. Then we can do the same thing. So this is our minimum. This is our most negative point. If this is our most negative point, what's happening to this point? It's increasing, yeah, because the maximum has already gone through. So we actually have positive vorticity advection on that side, and that's related to our rising motion. And then on the other side, since the negative is approaching, we have decreasing vorticity with time, and that sinking motion. So if you've ever wondered why on a jet streak chart like this, you have these opposite quadrants with rising and sinking motion, you can explain it with QG, just simple omega style QG like that. There's actually other types of circulations that are ongoing, and you'll learn more about this in dynamics, but this is a really simple way to think about vertical motion in jet streaks using QG. And sometimes in the real world, you actually get jet streaks that align. So if we've got another jet streak down here, remember we got rising motion in this quadrant. We've also got rising motion in this one. And so when they overlap, like on this, you actually kind of double up. You put your both areas of rising motion together, and that can actually cause really substantial height rises. And thinking back to our thunderstorm ingredients, that's a lot of lift that you can generate there. So,
All right, I guess we are pretending that QG's done. You can flush all that. I'm going to ask all of you a question here. Why are you here getting a meteorology degree from OU? Anyone care to answer? And if you don't answer, I will call on people randomly, even in the back. Okay, yeah, they're in the back. Okay, what do you want to do with the meteorology degree? Okay, anyone else? All right, well, we'll go in the back first.
I mean, main reason I'm here is just because I'm really fascinated by it. It's like I want to learn more about meteorology.
Okay, any ideas what you want to do with it?
Either forecasting or aviation.
Okay, and then we'll jump down. How about you?
The program is good, and I want to go to the SPC.
Okay, there, now see, there's the winning answer so far. No, I'm kidding. Well, look, the whole point of me asking you that is I understand, you know, I was a student, it was a long time ago. Like I last was sitting in here and like when it didn't exist. So it was before Sarkeys is when I was a student. So if that tells you anything, so we've skipped by a couple of buildings, but the whole point is it's easy to get caught up in the grind, worrying about what's due next week, how do I get through this semester? If you never sit down and think, hey, where am I trying to go with all this? Don't graduate and have that be the first time you've even considered what you want to do. You know, I think of the old video, you know, what do you want to do with your life? Seriously, answer the question. And only you can answer it. And then I would say that no matter what you choose, whether you want to get into research, whether you're just fascinated, you want to work at SPC, the better you understand this stuff. This isn't about just a check mark on a resume where, oh, I've got a meteorology degree. I view it as you're given a toolbox and you're developing tools. If you can't do anything with those, like you're pulling tools like, yeah, I know this is a tool, but is it a hammer? Is it a drill? Whatever, and you're just throwing stuff over your shoulders, that doesn't work. And if you come to SPC and that's how you are, we're going to chew you up and spit you out. That's just the harsh reality. It's going to be a tough transition. So think about what you want to do, why you want to do it, and then just realize that I love OU. I'm an alum, got my master's here, and this program will not alone prepare you for the real world. It just will not. You're going to have to do a lot of that yourself. So everybody who's here, I applaud you for taking the time out of your evening to show up. I mean, you could say, oh yeah, we're volunteering. So are you. I know every one of you has something better to do than this, presumably. Or maybe some of us don't have anything better to do, but that could be why. And that's really the only reason I'm here is I literally couldn't think of anything else to do but hang out in Norman for 12 hours today. But so anyway, give it some thought. If you have questions that you have about what it's like in our specific part of the career path, they may only sort of mention it in passing. The severe weather class, I was involved in helping create that back in 2015. And the two Andrews and Kelton shows up maybe in there sometimes, Harry Weinman, but those three, Harry, Andrew, and Andrew primarily are running it now. What's the common thread? And this is for you, Mr. SPC. What's the common thread with all three of them? Where do they all work? SPC. What class did they all take? The one that they're talking about for the spring. Who was an instructor in the class? Me. What happens when a resume comes across and you know more about one candidate than you do all the other ones? As long as it's good. Now, if you know more and it's not good, that's not going to help you. But so the idea here is you get for some of you, you're going to probably look at me and say, oh yeah, you're outgoing or you love to sit and talk in front of people. I'm not an extrovert. I love weather. If you just made me sit up here and talk about investing, I mean, I could say stuff, but it wouldn't be perhaps that useful. But the idea is you step out of your comfort zone, approach people. I think anybody's going to bite your head off. We're volunteering to be here. So that shows that we're interested. So if you have questions, whether it's grad school, you want to get into applied research, whether it's an operational forecasting job, whether it's something in the private sector, you still need to know the meteorology. So I'm just imploring you to put in the effort. I didn't have the dry erase boards. I didn't have PowerPoint when we did. We were drawing on a chalkboard literally, but spent hours and hours and hours talking through these things with people who ended up being my coworkers, like a handful of them from OU that now work at SPC, the geezer crowd. But anyway, just take advantage of your opportunities. But if you're hoping that OU is going to spoon feed you a successful career, good luck. Take advantage of what's around you. There's a tremendous opportunity here at Norman, but you have to take advantage of it. So I applaud you for coming in this evening. This is a good starting point. And let's see, we're not in present mode, are we? So let's get this going with the slideshow. So we're going to talk, I'll try not to drone on too much about the stuff. I know it's a lot of material tonight. Some of you, I know that a couple of you guys must be grad students, right? So y'all are chiming in all the time. It's going to be some of this is going to be, yeah, he's just talking about crap I already know. And some of you be like, wow, I've never really thought about it. It doesn't matter. I guarantee you everyone here can learn something. And if you think you can't, I'm going to invite you up here to teach the next session, and I'm going to sit in the audience and ask questions. So we can do that if you want. Okay, anyway, we want to talk about skew-ts. Andrew showed several examples of them in there, but it's been my experience that people don't understand the diagram very well. I don't know, I'm not sure exactly where this comes from. Maybe it's because it just isn't used in class much, but okay, this is the skew-t log P diagram. Anyone have any idea what the purpose of this diagram, the way it's constructed? What are you mainly trying to get out of this? We've got temperature plots in red, the dew point temperature in green, and then of course we got a wind profile. We're not going to talk much about the wind part of it tonight, but what is it about the orientation of the diagram that matters? Any ideas? Yeah.
You get a vertical profile of the atmosphere.
Okay. What does that tell you? What kinds of things can it tell you? Right, and then what can you forecast with a sounding?
You can see where the atmosphere is stable or unstable.
Okay, and we'll talk a little bit about what that means. Anything else? Is there any kind of weather that a sounding's irrelevant for? Can you think of one? Fire weather? Totally relevant. Winter weather. As much as deep moist convection, if not more so. So the idea here is that this diagram has been designed to highlight buoyancy. There are other ones like other countries, the Tifagram or whatever. It's the skew-t. This one exaggerates the look of buoyancy compared to other thermodynamic diagrams. So this is a thunderstorm centric type approach. So we send the balloon up, you measure the temperature and the dew points all the way up, you track it to estimate the winds. And so there's a bunch of stuff on this diagram. And so it's really not that complicated, but if you don't know what the contours mean, you're not going to be able to get any of the concepts that this diagram can illustrate. So pressure or the horizontal lines, that's a constant pressure. So in this case, it'd be 200 millibars or whatever it is. And so you plot them. Now, where does the log P part come from? Any ideas? Because remember, all the horizontal lines are pressure. Yeah. Yeah. And so what happens? I mean, the pressure increases logarithmically or decreases logarithmically as you go up. The pressure contours of the same interval get farther apart. The atmosphere is more dense at the bottom than it is at the top. This is a way to illustrate that. All right. This one's an isotherm. So we talk about, do you think people are very careful when they say things like an inversion or whatever? How would you define a temperature inversion now that you know the slope of a constant temperature line on this? Are there any inversions on this profile?
Yes, two. Really three, but there's.
So there's, where are they? Tell me where. We'll start up at the top. I'm going to start going down. You tell me when I'm getting. Okay, kind of in there. And why would you say kind of?
It's troughs.
It's close. It looks like it's roughly isothermal. It's parallel to the temperature contours. Okay, so that one's a maybe. We go down any more? Okay, there's an inversion. So the slope of this, it's tilted more to the right as you go up. The temperature is not decreasing at the same. So this is a case, an inversion is where the temperature actually increases with height, as plotted on this diagram. And then we go down, and the more standard that everybody be focusing on there is a classic temperature inversion at the base of what we call the elevated mix layer. Okay, so you can plot temperature on there. You've got pressure. You've got constant mixing ratio. Now, mixing ratio isn't the dew point. It also includes the effects of pressure. Is anyone familiar with what would be the same equivalent dew point at Denver compared to right here? Do you need the same dew point temperature to have the same mixing ratio? What's different in Denver about here compared to here? Yeah. Altitude. So what does that do to the surface pressure? It's a lower pressure. And if you look at the slope of the mixing ratio lines, I mean, they're not, it doesn't follow the temperature. It's actually offset. So you actually increase the mixing ratio as it's a function of the pressure. So the same dew point has the same impact, or a lower dew point in Denver has the same relative effect thermodynamically as a higher dew point would here. And it's like 8 or so Fahrenheit at least. So I don't know, you could figure it out. All right, other ones, a dry adiabat. What's a dry adiabat? Who all's seen the ideal gas law, any of that? We're just ignoring moisture. So yeah, this is the rate of change of temperature with height for unsaturated ascent. This is the balloon. It rises and expands. How quickly does the temperature decrease if there's no clouds, no condensation? So notice, is it a straight line? No, it's actually a slow curve. So if you're comparing, if you want to say the lapse rates, the change in temperature with height is dry adiabatic, you're saying it's paralleling one of the dry adiabats. Now notice the difference, the skew-t comes from, look at the difference between the isotherms and the dry adiabats. It's a pretty big angle there, 60 degrees or something like that. That's what allows you to depict buoyancy better. If that angle's smaller, it's not so obvious. All right, and then the purple one, anyone, what's that called? Moist adiabat. So this is how we represent saturated partial ascent, the latent heat release. Does the temperature decrease as quickly when you have condensation and latent heat release? No, because as you're condensing water vapor, you're changing phase, you're releasing energy to the environment. So this, in this case, the parcel, it keeps it warmer than it would be if it weren't saturated. Okay, so just understanding what all these lines mean are how you illustrate the processing. So if you just, I would say, take as much time on this on your own, we don't have time tonight, to make sure you understand what all of these lines, they're on there for a reason. Nobody just randomly, yeah, I'm going to screw with some students and let's just put this stupid contour on there. No, they mean something. Okay, so the common sounding terms. If lapse rate, who's heard the term lapse rate besides me saying it 30 seconds ago? Okay, good. I don't see anyone who has it. Dry adiabat, moist adiabat, these, I've given you the rough guess is what the rate of change of temperature per height per kilometer is. Dry adiabatic is, you decrease about 50% quicker than you do for a moist adiabat. Conditional instability, who's heard of that one? Okay, what is it? Even though it's plotted there, can someone tell me? Let's go back to the previous plot, how would a contour be oriented that's conditionally unstable on this one? I'll hint. The hint is it's referred to the magenta and orange line or curves. Where would it lie? All right, between the two. That just means conditionally unstable means you have to do something to the if you apply ascent to the profile, you can actually create buoyancy. But all right. So anyway, the LCL height, the level of free convection, the equilibrium level, Cape, convective inhibition, are any of those terms like, is there anyone who hasn't, it's hard to believe here somebody hasn't heard them, but is there anyone who has any questions about those? So I'll do some illustrations. And again, throw the questions out. There is no stupid question. The stupid one is if you don't understand it, you don't say anything. Because, all right. So here's a profile. This was a fancy, well, for me, a fancy animation, but in PowerPoint, but I was too lazy. It wouldn't convert to Google Slides. So you're just going to have to pretend that I'm animating this. The idea of lifting a parcel, we're starting right at the ground. Any of you weather weenies know what this, recognize the profile this day? Which one is it? Which El Reno?
The 2011.
Is it? Anyway, just think about that. Keep that in mind. Yeah, if we have some time, I have a fun exercise we'll do at the end. I don't know if we'll have time for it, but the idea is that if you look in the low levels, this is an afternoon sounding. What's the lapse rate there? That's the rate of change of temperature in the lowest, few thousand feet on this profile. Say the lowest 50 millibars or 100 millibars, which is just the part down here. It looks like dry adiabatic. What's that reflective of? Unsaturated ascent. We'll talk about this. This is vertical mixing. What does the lapse rate roughly look like above that? Moist adiabatic. What do you think the sky could potentially look like? It could be stratocumulus or some that's indicative of a cloud layer. And then we've got steep lapse rates above. But the idea is with this inversion, we've got nothing to really inhibit overturning of air down low. But when you hit that inversion, that's our cap. Basically, you've got negative energy you've got to overcome. So the level of free convection is actually up higher. Now, the ones that are plotted here for the LCL and the LFC are for the virtual corrected lifted parcel. And I'm not going to go into that right now, but so it makes it look like it's uncapped, but you have to, if you look at that real closely, you see that very faint dashed red line. That's where that's being compared to, not the thick red line. So to get the Cape Sen calculations. Does anyone notice anything? Does the virtual temperature correction as it's plotted here, which is that's what you'd normally see on an SPC plot. This is the non-virtual. Any idea why those two would converge? What's the virtual temperature mean compared to the regular, like what are you including in the virtual temperature that's not in the regular temperature? Moisture. So it's the influence of moisture related to the ideal gas law. So we're accounting for the effects of moisture on density. So which basically makes it lower is what it, in effect. It shifts it to the right. What kind of environments is that going to make the most difference in? Moist, so like tropical, Arctic. Yeah, it's going to be high mixing ratios. That's the key. It's going to be these moist. So the more tropical, subtropical, or occasionally our May type warm sectors, that's where it's going to make a big difference. So anyway, these are things to make sure you understand the shaded areas. This one's just a depiction of convective inhibition and buoyancy for the non-virtual lifted parcel. Again, that's not the one, the virtual, the dashed white is what you would see like on the SPC sounding plot. So the point here is just think about how all this ties together. Because if you're stumbling around trying to interpret the diagram, how are you going to make a forecast up? That's kind of like me saying, oh, I've memorized the alphabet, but I don't know how to spell anything. You can't write a sentence with just 26 letters and you don't know anything else. What I'm saying, this is the equivalent of word structure or sentence structure that you need to learn. And then again, I just highlight the virtual versus non-virtual, whatever. Is this a profile that is particularly unstable if you lift the surface parcel? What do you see in that profile near the surface or just above it? An inversion. What if we go to a mean parcel? Why would it get more unstable for an average parcel if we consider a deeper layer? What's happening as you go up? Higher mixing ratios. So potentially the buoyancy increases. Well, what if you just take the worst case scenario? This is what we call the most unstable parcel. So you can see from this, Cape, it makes a huge difference what your parcel choice is. Is there any right answer all the time? No, and this is where you have to understand the environment to figure out what is a reasonable choice for the day. All right, so we'll talk about some of the processes because this is what I'm more interested in and what I would hope that y'all put more emphasis on is what does this diagram tell me? Not just what is it, but what does it tell me? Okay, simple vertical mixing, some pancake queue, some lame-o day out in the panhandle. I can't remember when that was, but little cumulus pancakes. This is a typical reflection of daytime heating and vertical mixing. You get these little convective plumes, they overturn, you get saturation at the top. And what are you doing when you're mixing stuff? What's the notion of mixing? Or what are you redistributing? When I say something's mixing, what am I mixing? Moisture, which way? In the vertical? Well, do you know? It's both. You can be mixing dry air down, relatively moist air up. You're redistributing heat and moisture in the vertical with mixing. So here's just one. I'll show some more soundings for this. These are just a typical, like a morning sounding on the left. You've got an inversion. You see a moist layer here. This one, I mean, this isn't necessarily meant to be totally realistic, but by afternoon, what kind of lapse rate is that in a general sense? Dry adiabatic. What kind of mixing ratio is that? Constant? So that's a reflection of mixing. Constant theta, theta is the dry adiabat. Constant Q, which would be constant mixing ratio. That's how you know this is a well-mixed profile. Is the sun out in all likelihood in that profile to the right? Has it been out for many hours during the day? Yes. You can infer that just from the sounding structure. Okay, so we go here. These are some examples. Here's just a typical August thing to show you that I'm not just making this stuff up. Here's a typical profile. And what happens to the temperature warms and what do you do to the low level inversion? We quote, mix it out. So you've redistributed heat in the vertical, roughly dry adiabatic. What have we done to the moisture? We go back to what it looked like. Notice there were higher mixing ratios near the surface. What happened to them? What happens higher up to the mixing ratio? It increases, so you're redistributing moisture in the vertical. Okay, and so this is what we call the mix layer. Now, the reason this stuff's important for thunderstorms, what is that also doing to convective inhibition? The deeper your mixing gets, you're steepening those lapse rates and you're removing whatever residual inversions which correspond to convective inhibition. And so this would just be like essentially the parcels are moving up. This is overturning. And a lot of times, what is this? Does anyone know the fancy term of what this would look like on satellite or radar? The term for there's specific structures you will often see when you have really good mixing like this. Right. So they're it breaks down into these mesoscale structures, HCRs, the fancy word. All right. So now there's an interesting thing here. This is a sounding from Flagstaff. What the heck's going on at the surface there, or very near the surface? Now we'll go back to this one before I put all the crap on it. Why don't you see that in the Norman sounding? The sun looks like it's been out all day in this one. Why is there no super adiabatic contact layer? It's actually a simple answer, but you have to think about why.
Well, this is past heating.
Okay, so what's a real simple way of saying that?
Oh, the sun's still out.
It's earlier in the day in Flagstaff. The sun insulation is still strong in Flagstaff. You are way past peak insulation. So the sunlight, there's less incoming solar radiation in Norman at 7 p.m. That's the equivalent here, it'd be more like 5 p.m. So it's earlier in the day. That super adiabat is what drives vertical mixing. It's not the dry adiabat, it's the super adiabatic contact layer where you get, does anyone know the term for that?
Absolutely.
It's absolutely unstable. And what kind of convection? Or something convective, auto-convected. This is where you get, because of the density imbalance, it spontaneously will initiate the overturning. Dry adiabatic won't do it. It just doesn't resist vertical displacement, but it will, you need the super adiabatic contact layer to actually drive the thermals. Okay. So, and again, just to prove, if you think I'm making this up, this is yesterday in Norman. Same thing. The sun was out, it's dry, it wasn't particularly windy. Now in this case, there's probably a few more things going on the moisture profile, but you look at the change, it doesn't change nearly as much aloft. Most of the changes are down low. Yeah.
Flagstaff and this one, there's a slight increase in view right towards the surface. What's the cause of that?
My understanding of that is the way the sondes are launched, everything above the surface is the balloon. It's the measurement from the Vizsla sonde, or what I think they're still using Vizsla. The surface dew point is calculated with a sling psychrometer at the site. And I guess the way the Weather Service does it, there's a known high bias. So those dew points are actually too high. If you
just put it in the ASOS value.
Yeah, I mean, so some people do that, but there's others where they can literally do the sling psychrometer, try to estimate the dew point right there at the shelter, right before they launch the balloon. And a lot of times there's a high bias on those. So you'll see, because it doesn't make sense, you'll see these little high dew point. And this is, if you're not aware of that, and that makes a big difference between like surface-based Cape and mean layer parcel, depending on how egregious those errors are. But no, it's a good observation. Okay, elevated mixed layer. Who's heard of it? Again, I might throw you out if you haven't, so pretend and just raise your hand. The elevated mixed layer, elevated from where? The heck is that supposed to mean? Coming out from the west. Okay, at the bottom, we've got a terrain plot that I'm assuming is reasonably accurate. I don't know. It looks a little jaggedy from me driving that. It wasn't quite that bad, but the point is it higher or lower in Albuquerque? Which direction is Albuquerque from here? West. What's the general flow direction? So look in the two soundings. It's generally westerly. We just talked about a mixed layer. You might say, why is this guy showing so many sounding, lame, dry mixed layer soundings? Who cares? Where do you think the elevated mixed layer is coming from? The only reason we call it elevated, it's elevated here at Albuquerque, it's just a mixed layer. There's nothing special about it. And if you just look at you take the lapse rates that are being generated by surface heating and mixing over the higher terrain, and this is just horizontal advection, that these are displaced. The only difference is that over here, we have lower elevation, and there's a whole bunch of reasons behind this that maybe eventually we'll get into it, the whole differential advection thing, but the air in the low levels is coming from somewhere else. What's upstream from Oklahoma to the south and southeast? Is it a cold ocean basin? No, the water temps are in the low to mid 80s right now. So offshore, away from the shelf waters. Point is, there's a moisture source one area, you've got slope terrain, you have a lapse rate source somewhere else. The height of this terrain also matters as to how deep that mixed layer gets. So it frequently mixes as high as 500 millibars out there over, and there's a big area. It's not just like there's one mountain. You get to Albuquerque, the terrain is pretty high, 7,000 to 10,000 feet everywhere to the Sierra Nevada. So there's a huge plateau with the potential to generate these lapse rates. And this, all you have to do. Okay, another way to look at this is, you remember a dry adiabat? What's the fancy Greek letter that we use to represent that, a dry adiabat? So well, that's the lapse rate. But what on the diagram, what is a line of constant what? Potential temperature. So what do we use? Theta. Well, guess what? Theta is just the temperature if you take it dry adiabatically down to 1,000 millibars. That's essentially how hot is it getting, and you can project that seasonally what it looks like. So if you take something from the vicinity of Albuquerque early April, this is the dry adiabat that's typical, normal temperatures in the 70s or whatever. They warm into the 80s, they warm into the 90s. It just shifts it to the right on the diagram. Same lapse rate, but you shift it to the right. Does that make a difference?
Yes.
Makes a huge difference on Cape and Cent as to how far right you are. So in some sense, how many of you have ever thought about a chase day and I said, I wonder what the mean theta is going to be in the next 2 or 3 days over New Mexico? Ever thought of it? You should. Because if you want to project what these profiles are going to look like, that's your source region. It's just as important as looking down in the Gulf and Caribbean for the moisture in the low levels. Okay, other thing, influence of lift. What does ascent do to the profile? In most scenarios, if the lapse rates are not dry adiabatic or steeper, what is it going to do to the temperatures? It should cool it. The rate at which it cools it just depends on, if it's a more stable layer, it will cool more rapidly than a steeper lapse rate. So if you just look at what this would do, these are real soundings, by the way. This isn't some modeled thing. These are actual observed soundings. Does anyone recognize the date? Super Tuesday. I worked the day shift for that one. This is what real world ascent looks like. Modifying the profile, the moist layers deepening from below, the morning inversion, we go back, I don't spaz out, is, people say it's lifting the inversion. It's basically you're cooling and moistening from below through that layer. And you notice on the little inset to the right, it shows you where you are with respect to the cyclone. So there's ascent and if you look at the temperature contours, you could actually work your way backwards. Where's the trough in the upper troposphere, middle and upper troposphere? Where would you infer that it is compared to this? Just to the west. All the strong cold advection is just west of there. That's where all the height suppression should be. There should be a trough. And given the fact that the ridging, see, in other words, when you start thinking about it and piecing this all together, you can actually work your way from relatively little information back to coming up with a pretty good first guess as to what the pattern should look like. It may sound stupid. Well, why do I need that? I can just look at the HER UH tracks. I mean, there's people that think that. And I said, okay, if you think that you're going to get paid like 6 or 7 figures yearly to say, look, red UH. Please give me a call. I'd like one of those jobs too, because it's pretty easy. But the point is you've got to be able to add some insight. And you're not going to get insight from like literally showing something, hey, look, here's some convection allowing guidance. That's not value added. So the point here is you can anticipate modifications to the profile. Obviously, if we get a chance, we're going to talk a lot more detail about how you would use this severe storm forecasting. But the point is there's a bunch you can do. There's also differential advections or changes just due to temperature advection over time. Here's a profile up where the dot is up at Topeka. This is what it looks like. Now, is this a scenario where you would think the profile should be static over the next 12 to 24 hours? First of all, where's this trough that's depicted? Where do you think that should go? Just using QG arguments, where should it go? Northeast? East, northeast? I mean, I'm not asking for anything, but it should be moving.
Yeah.
There are lots of advections that are inferred from this sort of pattern. Okay, indeed it does move northeast. Look at the change in the profile at Topeka. This is just due to changes in the thermal structure related to the progression of this intense mid-latitude trough. I mean, you've changed just about everything. Another interesting one, notice when he's talking about with the differential thermal advection, suppression of the thickness, what's happened to the height of the tropopause? Oh, look how much lower it is. It's down just above 500 millibars. We have shrunk the column because there's been so much cooling down below that. But think about that. You've cooled the column, but you've actually destabilized it. This is how you do that. All right. So other examples of the same kind of stuff. Here's some real world soundings from Norman. Now, the important thing is Norman is upstream. Does everybody know where Lamont is? north central Oklahoma. So it basically just goes straight north up toward the Kansas border, and that's Lamont. So Norman sounding, moist layer, steep elapse rates in the mid levels, but a big inversion. We go to Lamont, pretty similar, right? I mean, there's some minor differences. Okay, so in this sense, do you think is there anything that would suggest, and what's the wind direction at both Norman and Lamont? Or yeah, generally south. That's all I'm looking for, is it's kind of a southerly wind. So is there more moisture upstream from Lamont? Is there?
Downstream.
Upstream from Norman's upstream to the south. So the air's blowing from south to north. Is it more moist in Norman or not? I mean, a little bit, but is that a big change? Do you think this is a profile where it should be really cloudy? How would you answer that question? Looking at sounding like this. Start aloft. First of all, is it saturated everywhere? No. So probably not a ton of mid and high clouds. Could there be down low? I mean, maybe, but is that saturated? This is a 12Z sounding. Is that particularly moist for 12Z? No. So there may not even be any stratus. So this means it's probably going to be a pretty good heating and mixing setup. So when you look at what happens at Lamont, what does that look like, the moisture profile? Normally it's like, oh yeah, we got south winds, the moisture is going to increase. Look at the actual setups. In this case, and then here's another interesting one. I've plotted the mean 100 millibar mean layer parcel. Is the Cape increasing? No. We continue to 0Z. What has actually happened to the buoyancy? It's gone down with daytime heating. And why is that? The moisture, look what happens to the moisture profile. Yes, it's redistributed in the vertical, but we're not advecting enough moisture horizontally to offset that. So what happens is regionally, the moisture is mixing upward and dry air is mixing downward, but it's not being replaced. That's not necessarily the case everywhere in the region. Does anyone know the date on this one? I mean, this goes back a little ways, but y'all are pretty young, I'm guessing. Yeah, there were a bunch of tornadoes right near and after dark in western Iowa. So this is the Topeka sounding. What kind of boundary at the surface do you think is very close to Topeka at this time? And why? Strong inversion. Moisture increases with height, but it's pretty warm up above that. Here's Omaha. Are we farther from the cool air source or deeper into it? This is the frontal inversion, this whole thing. So it's like, aha. So now you look at the profile at Topeka. What's different about this compared to comparing Norman and Lamont? The moist layer, much deeper in Topeka. Is that going to be more resistant to vertical mixing?
Yes.
Okay. Here's what the sounding turns into. And, you know, you started from this and turned into that one, or actually I went the wrong way. You started from this one and turned into that one. Am I forecasting tornadoes at 12Z looking at that?
No.
I hope not. Maybe a different case here. There were significant tornadoes after dark. So, and we'll ignore the other things that have happened with the wind profile, but you notice warm front lifts north, there's cyclogenesis to the west. The changes, you can anticipate these things. So if you're looking at model soundings, how do you judge the quality of these things if you don't know the processes? Do numerical models have perfect boundary layer and radiation schemes?
No.
Yeah, I mean, because why else? All I can tell you is look at the RAP and the NAM and just compare just those two and look for the same time and location and pick in the open warm sector and look at them. There are surprising differences. And the question is, the numerical modelers, are they going to lose a lot of sleep and say, you know, so what? Your dew point's off 5, 6 Fahrenheit. They're not losing any sleep. I'm not sure. They're maybe not happy about it, but they're not going to be worrying about your precious warm sector. But the question might be that 5 degrees might be the difference between storms and no storms. It could be the difference between tornadoes and a few stratocumulus clouds. And do those kind of things matter as an outcome? I can guarantee you that in more, they'd rather it be stratocu than a tornado. So anyway, I just wanted to go over that stuff. How, I guess we were gonna go to 8. I have one thing I can do. Now, this one isn't fair, especially to, well, it's not fair to those, I'll take it out on the grad students here, but this one should be no holds barred, but okay, some of you, I know that we haven't talked about all the details, but I want to play a game with the soundings. It's a very simple one. Let's, yes. Oh, I expect correct answers out of y'all. No, where is that one?
It might not be on there yet.
Oh, you didn't. Yeah, so if you gotta go, I'm not gonna be offended, but we're gonna play a sounding game. It won't take but 5 or 10 minutes, but.
Yeah, I got a meeting at 8:30. Yeah. I did notice that we had that.
Did you send it over? Yep, there we go.
We don't always have our act together, early, but close enough.
That's the first one, you know.
Yep. Okay, if you choose to accept the challenge, and if you do, you cannot leave midstream. Nobody gets mad and runs off. You have to stay for the duration of this. But again, no more than about 10 minutes. Very simple question. I'm going to show you a sounding. These are all real soundings. And you have to tell me, was there an EF3 or greater, a high-end intense tornado within roughly 100 miles in 1 hour of the sounding? So, it's a proximity sounding game, but all you have to tell me is just intense tornado or not. Easy, right? And tornado forecasting is easy. So this should be. And then I'll start and ask you, and I purposely put the picture on here. Is this a picture of an EF3 tornado or not?
I would guess no, because there's not a lot of.
What is it?
But is that the question, really? What do we mean by, is an EF3 plus tornado? Do we mean what its wind speeds were, or what it damaged?
Yeah.
I'm just saying that by itself, the answer to the question isn't always that obvious. Could this have been, by the way, it was rated EF2. You can tell from the foreground, did it hit anything? Hardly anything was affected. Does that mean this wasn't an EF3 plus tornado? This was May 23rd of 19 out west of Canadian. So, okay. So here we go. And you notice you don't have the dates. So I challenge any of the people that can memorize every sounding out there.
I won't say anything.
At the end, but EF3 plus tornado or not?
No.
Everything was
By rating, no.
yeah. But
Okay, if you're going to say no, I want to know why. Not just, oh, I remember this case and it didn't happen, or you think you remember it. Why? Tell me what's wrong with the profile.
I don't love that convergence over just below 700 millibars.
Okay. And what's the relevance of that?
Don't love it.
Any other?
I mean, but.
that sounding is popping.
Yeah.
Okay. Is it too good to be true? Do you think I'm like trying to pull a fast one on you? That
Probably, because I know they.
I might be.
Yeah, that sounds.
I'll put it this way. If you're trying to guess the pattern that I'm giving you in the soundings that are presented, good luck. But because if you think that I won't show 10 in a row of one type, you can assume that, but. Okay, so what's the consensus? I've heard a couple of no's here. I don't like it. Does anyone like this sounding? This sounding needs to feel some love. Does anyone? You like it? Okay. Okay, so is there anything that, I mean, again, let's show of hands, EF3 plus or not? So there's a few. So EF3 plus, so no way, this is the lamest profile and I'll never, ever chase if I see something that looks like this. Well, we said there's no tornadoes. Okay. It's a no. Okay, does anyone know what profile this is?
It's a 0C.
Right. What was the thing that was missing? So this is a problem with a game like this. I didn't tell you if there would be a storm. Do we know that this profile would not support an EF3 plus tornado? No, because we didn't get to test it. Okay, what about this one?
There's gonna be, it's gonna be some closely.
Well, but it was too far away and too far, it was outside the proximity window, so doesn't count. All right, any guesses? Who's the brave first guess? And not you guys, that was someone else. Yeah, well, I'll let you guess. Someone else. Let's have somebody new who hasn't provided a guess. Give me yes or no. EF3 plus.
I'll go yes.
Okay. Any others? Yes. Okay. Let's see all the yeses for this profile. Okay. I mean, am I right? That's a little bit of a majority. How many no's? Just so I. Well, some of you aren't raising your hand. Does anyone remember this? You probably don't remember it because now I bet you do. This was January 22nd, 2017, Jacksonville, Florida.
Oh, that was a higher.
There was a 1.25 mile EF3, high end EF3 with a 75 mile track, but it was too far west to count for this one. It was earlier and farther west. So just like in these two cases, remember the rules do matter. So some of it. What about this one?
Yes.
No, that's, yeah.
Well, I mean, you know, what's so great about this one? I've given you two no's. Why would I change now? I mean,
the last two were almost a yes.
almost a yes. Well, they weren't anywhere close to a yes within the proximity criteria. It was nowhere close within 100 miles.
I could argue maybe the upper level of the graph is not as,
Do you think you'll have storms with this profile?
Yes.
I mean, what? It's saturated all the way to 500? I mean,
Right. That's what I'm.
oh, veer back. Does anyone think they recognize the day? I'll just ask that since I know I have some chase weenies. Okay, you think you do? When we give the answer, I want to hear what the day is. So, okay, so this one, most people are saying yes. EF3. Okay, what day was it?
May 17th, 2019.
There you go. This is the Dodge City Sound from the and it was the Mineola, Kansas EF3. Yes, this was the far southern supercell on that day. Okay, what about this one?
Yes, double digit.
Crazy thing though is that
This is one of the greatest topics I've
So obviously you guys think you know which one it is. How many yeses? How many no's? Okay, now it's not just EF4. This is Birmingham from 0Z April 28th, 2011. Just 0Z on the 28th. There are on the order of 24 EF3 plus tornadoes within that proximity criteria. So, yeah.
Like the dew point and the temperature kind of like a little wobble, where it indents, it like goes out and then
Right. Is it this part? That could be this. That could be the sonde went through some strato Q or something, and it got damp or whatever.
Above that, it does like full like right.
Yeah,
Is that some sort of?
it could just be an artifact. It's a good question. I mean, I don't have the answer specifically on that one. All right, are y'all feeling good about your ability to guess these things? It doesn't get better. What about this one?
No.
Okay, so we've got a yes because you think it's no. How many of those? How many say yes because you actually think it's no? Because you think I'm just trying to fool you. How many say no because I know how to interpret these profiles? And I say no. How many say I have no idea and I don't know how to interpret these profiles? EF3. Does anyone know this one? It wasn't that long ago. It was this month, 2019. Within a 3-hour drive of right here. It's the Dallas-Fort Worth tornado. What about this one? All right, I'm going to ask one simple question first. So we're going to simplify this one. We'll get to the EF3 plus part. What time of year and where do you think this is? Just in regionally, what region of the U.S. do you think this is, and what roughly time of year? So I mean, is this like February? Is it a spring? Is it a winter? Is it a fall? Summer? So I've heard some late spring. Pop tropical cyclone, maybe?
Yeah.
Anyone think maybe this is a tropical cyclone? Okay, there's a few. Okay, so let's get down to it. I don't want to hold y'all too long. I do have a few more to go. Yes or no? EF3 plus. Okay, and okay, that's a good one. So we had it here. It was mentioned they don't think this is a tropical profile because of the wind profile. Care to elaborate?
Well, if you think about a tropical cyclone, the winds actually tend to decrease with height, right? You have the strongest winds.
Well, when you get to a baroclinic low, like the stuff we're talking about with QG, what sort of low would we call that? Cold core or warm core? Cold core. So what's the difference with a warm core low? And you have higher heights aloft, weaker gradients. If you've ever looked at atop a hurricane, especially an intense one, what does the flow look like in the cirrus atop the hurricane? It's divergent anticyclonic. You're building a high up above the hurricane core. So these winds are pretty strong. You can have a strong flow way up high in the outflow away from that, but 70, 80 knots all the way through the troposphere, that's pretty unusual to see that kind of profile in a TC. So this is not a tropical cyclone. Okay, so what do we guess? Yes or no? I only heard spring. I didn't hear, nobody was confident. So we'll say spring, close enough. What part of the country? I heard Dixie was the only. Okay, I've got a winter. We've got spring or winter. What's the vote? Which one is it? Spring or winter? Okay, we got Arkansas, very specific. So it's in Arkansas. How about I tell you this? I will tell you that will you think the state will help you? South Carolina. Yes or no? I've given you too much information. I agree to this. So you're telling me you would have no qualms about this profile if it's a chase day here in Norman? Nobody's gonna be complaining about the lapse rates aloft.
I mean, there's.
So, okay, the final call, yes? EF3 plus, yes? No. This is actually one of the two most intense tornadoes on record in the state of South Carolina. Do you know what time of day this is? This is a 12Z sound. April 20th, the Easter or whatever, April 12th or 13th of 2020 during the pandemic. So this was the EF4 northwest of Charleston, South Carolina in the morning. I was working the midnight shift when this one happened. So, all right, what about this one? Yeah, okay, what would be a hint as to what part of the country this profile has to be in? Okay, what else? There's an easy one that would give you a hint of where, is this on the Gulf or Atlantic coast?
No.
Why? Yeah, you've been to Galveston. I assume some of you have. It's kind of at sea level, which is not at, 900 millibars. So so what do you think? Yay or nay on this one? So we know it's probably a higher elevation site. Yeah, the surface pressure is relatively high. So this is higher elevation. Yeah, is this near Norman's latitude or is it west of us? What's a typical surface pressure here, like for the Norman sounding? Yeah, 970-ish. Obviously it varies, but 970. This is lower than that. So this is somewhere to the west at higher elevation. All right, yes or no? Yes. To the nose. Yes. Yes for no. EF3. This one is the evening sounding. I don't remember if it's Dodge City or Amarillo for the November 2015, November 16th of 2015, the early nocturnal high plains outbreak. This is what those profiles look like. All right, what about this one? What's not the love? All right, we're going to change it up for this one just for fun. Since we have the SPC contingent in here, we're going to put them on the spot. Oh, yeah. I want these two, Kelton and Andrew. I want your consensus, and you have to reach one. Cage match, whatever. It's I want a consensus, EF3 plus or not. I told you I wasn't going to let y'all get off too easy. Consensus is no.
There has to be a
I'll have to look. I'm trying to remember the date. I'm just kind of laughing. Yeah, but it was, I forget which one. I'll tell you on the side. Okay, what about this one? I could just be trying to fool you, or I could be just lobbing one up. EF5. Oh. How many votes for EF5 do we have? That's specifically EF5. It is EF3 plus. No. I'm not telling you when it is. Well, there is some missing wind data, but there's no reason to believe that that interpolated photograph is terribly wrong. All right, what are the guess? We've got EF5. Any no's? Anyone saying no? Well, no, I'm just saying EF3 plus. Anybody who says no to EF3 plus? No storms. Now, does anyone know the date of this one? I'll be impressed if y'all know this.
That's gotta be in the 90s to stay up.
Well, I mean, that's a good guess. When in the 90s? This was a high risk day. Come on now. What day? Nope. Well, the answer is no. So, I mean, I could have engineered that on April 26th, but no, the point wasn't to engineer ones where I'm just like putting it 101 miles away. This is the long lost April 11th of 91. It didn't thunder.
Nice.
What about this one? Well, if you keep saying it, you'll be right. Better guess. Now it would be called the F5 now. Now here's the important thing to know. This is easy when you know the answer, and it was a tornado right down the road. But that is a real profile with no thunderstorms. You tell me that you're going to be with 100% confidence, you know that, oh, that's clearly this day's the violent tornado. I worked the May 3rd event, the day shift. It was not a given that there were going to be thunderstorms. So, all right. So we can, I only have a couple more. What about this one?
Yes.
No.
Yeah.
Well, first of all, this is an observed sounding. So is it Hastings? SPC forecaster fail. That was. These are observed soundings. So this isn't a model sounding. Just for reference, Hastings, Nebraska does not have a Rayop site. So the other Hastings, it's not the other Hastings either. All right, what is it? Yes or no? Of course. Oh, okay, of course. This is, you will bet. What's not to like about this one? And what about this one? Any yeses on this one? Any yes? We've got a rolling Fork, Mississippi from, I assume that was within 100 miles of a site, right? That's within 100 miles of Jackson, I think. I accidentally just drove through the damage path about 4 or 5 weeks ago, but I think it's within the 100 miles. That should be a hint, the fact that I'm asking you the question. Should be a hint that maybe it's not that one. Anyone think yes? Okay, we've got a yes. EF5 says yes. Is this one EF5? Not EF5. Okay. Any no's? Is there anything you don't like about this profile? Service inversions lame. I mean,
But like, if you
Southwest.
okay.
especially with that little.
The answer is no, but I qualify this. Does anyone know what this profile, what day this was? This has been within the last 2 to 3 years. This is the Mayfield. This is the Little Rock sounding. It took hours and way downstream from this before the storm got going. So it's a no, but it's a no with an asterisk. So there was a downstream violent tornado. Well, that's the rules matter. Anyway, that's all of that stuff. I can do this all day, but seriously, if anybody has any questions, comments, you hate the exercise, don't ever come back, send me an email. I promise I'll respond. Yeah. Yeah.